All right. Okay. So now the next topic is what's the order of accuracy of finite elements? Recall, like in finite difference and in finite volume, we all talked about the order of accuracy. And we, in both methods, we have obtained the order of accuracy through a Taylor series analysis, right? So in finite difference, we have said that, for example, u of I plus 1 minus ui minus 1. So this is an approximation to our spatial derivative. It is actually equal to partial u partial x plus o delta x squared. That kind of gives us that the central difference scheme is second order accurate. Of course, there is another component about stability, right, that comes in. And you would only claim the method as a good method if the method is both accurate and stable, right? So let's talk about accuracy for now, focus on accuracy for now. If you use finite volume, everything up to the integral form is exact. There is no approximation. And the approximation comes when you want to approximate the flux, right, using just the volume averages. We also have derived, for example, the flux at u at a particular interface. And in finite volume, we denote the interface as I plus half, right, with the fractional numbers. We know it is equal to the function valued at the average of ui, which by itself is a volume average, and the ui plus 1, which is another volume average, plus o delta x squared, right? Well, I think we actually did was that we know that u at I plus half would be equal to half of ui plus ui plus 1 plus o delta x squared, right? So that's I think what we have analyzed. So yeah, let's forget about this for now. So it really we can say that, and if we have this, and if the flux function is smooth and continuous, we can then also claim that the flux approximation is also second order. So essentially, in finite volume, we have been doing a different kind of accuracy analysis for the flux approximation, how to approximate things on the interface with things that are volume averaged on the different sides of the interface. Now, for finite element, neither these two approaches actually work, right? Because we never actually approximated a differential operator. We have been applying the differential operators exactly in finite volume schemes, in finite element schemes, right? Remember, we have these basis functions that are head functions, and inside the integrals, we have to take their derivatives, and we have been taking derivatives analytically, because these are piecewise linear functions. So there are no approximation there. And we are also not approximating the interface values with the volume averages, right? Actually, we know exactly the values of our finite element functions anywhere, because they are actually piecewise linear and continuous functions. Not only they have exact values anywhere, their exact values are actually pretty easy to compute even. So where is the approximation in finite element, and how do we analyze their order of accuracy? That turns out to be a much more difficult question than how to analyze the accuracy in finite difference and finite volume. It turns out the best way to analyze the accuracy of finite element is to look at how we actually approximated the problem. We approximated the problem by restricting ourselves, starting from a space of any function. Okay, the space of any function can be the solution, right? We were started by looking at a solution among all possible functions. And then we restricted ourselves to the space of piecewise linear and continuous functions. We also restricted the test function. We relaxed the criterion that the weak form has to satisfy for any test function. We relaxed it to that the weak form only has to be satisfied for any test function that is a linear combination of the finitely many basis functions. So this procedure is actually the step that we are making approximations. Okay, and these approximations turns out to be the best approximation in certain sense. So finite element has a built-in sense of optimality in it. Just like in our first lecture discussing finite element, we have kind of derived it from a minimization point of view, right? And it turns out that the solution we get, let's say you had finite element, okay, is the best in certain sense. And I'm not going to explain to you this certain sense because it's actually a lot of mathematics. Is the best in certain sense for approximating the U analytical exact solution. Okay, so the analysis of how much error does finite element makes really ultimately comes down to what is the closest function within the restricted function space to the target function. Okay, so the finite element error analysis basically comes down to what is the best approximation. So for example, let me draw a quadratic function. All right, let me draw let's start with the quadratic function. And I want to say that if I just have a single element, the whole space between 0 and 1 is one element. And I want to approximate this quadratic function with a piecewise linear continuous function, which in this case, because I only have one element, it's a linear function, right? So let's say this blue is the best linear approximation to this quadratic function. Now the question is, how accurate is this approximation? What's the maximum difference between the blue line, which is the linear function, and the quadratic, which is the green line? Okay, and particularly we're interested in not just this question, but particularly if we are able to now split this element into two elements, and I can refine my best approximation. My best approximation now becomes probably something like that, right? It's even a better approximation. And if I keep refining, how fast do I approach a zero error solution? Right. So this is really the crux of a finite element error analysis, is to bound the error that could be made by the most accurate approximation. And in this case, it turns out if I split the elements into spaces of H, so let's say H is the spacing between the left and right boundaries of the element, and I have an arbitrary function, and the best piecewise linear approximation turns out to be OH squared, okay, is the best approximation error. this can be actually seen by just connecting the dots. If I just connect the values of the function at the two ends and connect these into a piecewise linear function, right? I mean, if the function continues over here, I can further connect the dots here and here. That's a piecewise linear and continuous function. Of course, it's not the best approximation. The best approximation would move this point upward a little bit, right? It would further enhance the accuracy. But I'm just trying to get an upper bound. Okay, we know the blue is actually either the best solution or worse than the best solution. So the best solution is going to be better than the error I got from the blue. And the error in the blue is already OH squared. And the analysis hinges a little bit, it's not that as easy as what we can do in finite volume and finite difference. It hinges on the mean value theorem. So the mean value theorem, it's essentially saying that this slope actually has to coincide with the first order derivative of the line somewhere inside this element. And then you have to base on the Taylor series analysis on that point. Okay, and basically by doing that, you can argue that the maximum error within this element is going to be on the order h squared, because the only contribution is going to be coming from the second derivative. You already matched the first order derivative. Okay, so basically by going through this procedure, you can prove that if you use piecewise linear approximation, piecewise linear and continuous approximation for finite element solutions, and this best approximation actually, the sense of what is the best actually depends on the differential equation, right? So for the kind of Poisson equations we have been solving, it's the easiest one to prove that the finite element approximation is OH squared or O delta X squared. And this is just to give you a sense of what goes into such mathematical analysis for the accuracy of the finite element solutions.